Alrighty. Welcome to our first meeting, we'll say, for this semester. So I'll start a little bit, I'll give a minute or two for people to figure out how to use Twitch. I guess it's not that hard, but just in case. Um, let's see. So today, for the first couple of weeks, actually, we're going to have two classes kind of together at one because the material is identical and it really doesn't make sense for me to make two videos for the same thing on the same day. So, yeah, so it'll be a little bit bigger population than normal, but that'll be all right. So, just so you all know, there's going to be a chat box on the right. You're free to use that whenever you want. Make comments, ask questions, whatever you like. Throw emojis in there for some reason. Look, here's a bee. Let's do that. Let's throw a bee at you guys. Where are my bees? There they are. Yay, here's a bee. If I did not mess that up. Okay, now we get two bees. Okay, hooray. So you can, throw stuff there if you like, ask questions. That's where I'll be seeing your stuff mostly. I typically am not looking at Discord during streaming time, so if you want to say something, best place is going to be there in the chat box. However, if any of you are watching this later, best place would then be Discord because obviously there's not going to be a chat box for you since you're watching a recorded video. Alrighty, I think that's enough time, so we can go ahead and kind of get started. So hopefully that kind of welcome video illustrated all of the class policies so I don't have to waste time going over those anymore. So we can start right with chemistry today. Hi, little one. We're going to hear potentially the little doggos running in and out of the room, so we'll see as they go through. So you might hear them. Cool. But anyways, let's start talking about chemistry. So chemistry is, not that you will ever be tested on this, but this is the study of matter. And so that's how it's most often defined, is as the study of matter and its changes. So how matter changes. That's all well and good, but if we don't know what matter is, that's a problem. We're using a bit of jargon here in our definition, so that's not going to be helpful for people who don't know. So let's talk about matter then. Matter is going to be any material, we'll say, and it's going to have just a couple definitions. Good morning. So we're going to see that often at the beginning of the chapters, we're going to have a lot of kind of vocab and definitions. I don't typically ever test on this sort of thing, but they are important for us to go over so that we're all talking about the same thing as we go through. So matter is going to be any material that has mass, or as we might say, an amount, something we can quantify. There's an amount of it. That's going to be kind of step one, and it will also take up space. I guess I need to put takes up space. Okay, there we go. And that's called a volume, which I don't know how to spell apparently. And so these are going to be kind of the two criteria that will define something as matter. And so we're going to see that pretty much everything falls under this category. We're going to see that we're going to be able to get a mass of pretty much anything, and we're going to see that things take up a certain amount of space. So my little stylus here, I don't know, weighs 10, 15 grams maybe. That's a mass. It has a certain amount of atoms in it. That's how we can talk about mass. And it has this kind of cylindrical shape that takes up maybe, I don't know, 10 milliliters or so. And so it's got a volume as well. It's taking up space. And we're going to see pretty much everything does that. So, clouds do that, air does that, liquids do that, my microphone does it, my body does it, my eyeball does it. Pretty much everything is matter. So we're going to see that chemistry, therefore, is a pretty big field because we're studying essentially everything. So almost everything is matter. And there's really only two things that well, actually, one category of things that isn't matter. And might be a little bit more obscure, but there's one thing that we deal with all of the time that you're dealing with right now in many, many ways that does not have, that is not matter. And that one thing, that one category of things rather, is energy. The only thing that we kind of don't consider matter in our, you know, lives, really, in our universe, is going to be everything else essentially. So anything that's not matter would be energy. So that would be light, for example, or heat. These are energies. Even sound waves are energy. So these things are not matter. They don't have mass and they don't take up any space. So as light rays are coming from the sun, um, they're not really taking up space. They're just kind of coming at us, and there we have it. Heat is a form of light, typically infrared. That at least our bodies, at least what we think of as heat, is infrared light. Then we're going to see chemistry-wise, we'd have heat as a different type of energy. Sound waves are pressure rates. That's more physics anyway, so we're not really ever going to talk about sound waves. But um, that's it. So we have everything as matter, and then energy is our only thing that's not matter. So oddly enough, while chemistry is the study of matter, we are going to be studying energy as well. So we are going to be studying everything in the universe here in this class. So at least at a basic level. So it'll be fun as we go through. So with that in mind, we can talk about some characteristics of matter that we may find interesting. And so we might want to kind of, seeing that matter is essentially everything, we might want to break it down into kind of easier categories. So kind of matter is a huge category. And so scientists have decided, let's make it a little bit easier. Let's see if we can break down matter into a couple of different kind of subcategories that are going to make it easier for us to talk about groups of things rather than just matter as a whole. And we're going to see that our kind of first division of matter, let's go ahead and break it up. We're going to see that if we take matter, which is essentially everything, we can really split it into two major categories here. The first one is going to be pure substances, and the other one is going to be mixtures. And it's actually going to be easier for us to talk about mixtures first. As we're going to see, this is the larger category. Most things are going to be mixtures, although in this class we're going to spend most of our time talking about pure substances. We're going to see mixtures, as we might just know from the word, they contain more than one, let's just say, thing. So for example, a mixture might be what I'm drinking now, coffee, right? Or what I'm breathing now, air. Air has multiple things in it. Air has nitrogen, oxygen, gases, argon, water vapor, carbon dioxide, dog breath, who knows, all sorts of fun different things in the air. So air is a mixture, right? It's got multiple things happening. Coffee is a mixture. It's got water. It's got all sorts of caffeine and various flavoring, delicious compounds, and so these are going to be examples of mixtures for us. Or we might say like a cookie, or this stylus that I have. Stylus. Let's try that one again. What else? A cell phone. Who cares? Whatever. All these things are mixtures. They have various different things going on inside of them. Pure substances are, on the other hand, one thing only. And so these are kind of less common, but these might be things like sugar, or salt, or water. What else might be a good example here? If you just have oxygen as an oxygen gas, that would be one thing, as opposed to air, which is multiple different gases put together. Let's see, we could have, what would be another fun example? I don't know, chloroform, that's one thing. So we're going to see here that for us to study these, it's kind of easier to study pure substances because we're only looking at one thing. Things get more complicated when we have multiple. Thought I heard one of the dogs eating something naughty, but I guess not. We're okay. So we're going to, as you see, because it's simpler to talk about pure substances, we'll be talking about those most of the time in the course here. But mixtures are going to be what's more realistic. We're going to obviously have a lot more mixtures in real life than we will have pure substances. A couple more might be something like copper or gold. At least 24 karat gold would be pure substance. Other gold alloys would have less gold. They'll have other things in them. Something like here might be steel, by the way. That's got iron and carbon in it. Two different things. Maybe some nickel, chromium, whatever. There are various metals going on in there. But hopefully not too difficult to kind of figure if something is a pure substance or a mixture. You just kind of have to think, is it one thing or is it multiple things? Something like, sugar, salt, or water, I would hopefully expect you to know is just one thing. Chloroform, I probably wouldn't. You've probably just heard of chloroform as something to knock people out in movies or TV shows. But it is a compound. Ooh, shouldn't say that yet. We haven't talked about compounds, but it is one thing. I wouldn't expect that for you to know that right away, though. However, the things that are mixtures, I probably would expect you to know all of those, maybe except steel, uh, just in case. But something like air, hopefully you can tell is a mixture. Hopefully, as you've gone through high school or whatever, you've learned that air is multiple gases put together. Alrighty, any questions so far on this stuff? I know it's not terribly uh, exciting to do vocabulary, but it'll be good for us in the long run. Alrighty. Moving on a little bit then. If we take a look in more detail at pure substances, we're going to see we can break that one down a little further as well. We're going to see that pure substances can be either classified as elements or as compounds. And for example, we have some elements that probably we're familiar, like oxygen, like copper, like gold, like silver, platinum, carbon, silicon, whatever. We have tons of elements, right? We have 118 total elements that will encounter, right? That's at least our knowledge of the periodic table has 118 elements on it. Um, Elements are distinguished by having, they only have one type of atom. And so again, this definition, we're using perhaps a word that we haven't defined yet, which is an atom. So let's go ahead and define that. An atom is kind of the smallest unit of matter. We don't really, we can't very easily break an atom apart, but we can separate atoms from other atoms. So that's kind of the like difficulty level there. Yes, with nuclear chemistry, yeah, we can break apart atoms, only certain ones. Oh, we'll definitely get to that, Michael. Sorry, whichever you prefer. We'll certainly get to that in just a second here. So we'll go through those. We're going to see that mixtures can have multiple compounds put together. Michaela, cool. Oh, okay, yeah. It's hard to tell where um, if it's where your last name begins. So I apologize. Michaela, got it. Okay. But yes, we'll get there in just a second. So we're going to see that way back in Greek times, um, they had actually come up with the idea of atoms is that you can keep, breaking a piece of copper wire in half or whatever, and eventually you'll be left with just one atom where you can't break it apart anymore after that. And that's where they kind of made that definition. So it's kind of the like you can't really break it apart anymore after this. Again, we really can, but we'll leave that aside. It's not under normal circumstances that we can break things farther than atoms. So suffice it to say, for something to be classified as an element, it has only one type of atom. That means the atoms comprising oxygen are essentially identical to each other. So all these atoms in a sample of O2 are identical to each other for our purposes, and so we'll define it as an element. A compound, though, on the other hand, will have multiple elements put inside of it. And so, probably our most common compound is water, which is H2O. That indicates 2 atoms of hydrogen and 1 atom of oxygen per molecule. If you're familiar with the periodic table, at least a little bit, you'll know that hydrogen is an atom or an element and oxygen is an element. In water, we have 2 elements, making up its kind of smallest kind of component there. And so we're going to see that every water molecule is identical, and each water molecule is made up of multiple elements. Another one would be something like salt, which is sodium and chlorine put together. Sugar would be another one. Oops. You don't need to know these formulas. Well, hopefully water and salt you probably know. And then, I don't know, something like hydrogen peroxide would be another one. Oops, that's H2O2. These all have multiple elements together, right? So we don't have just carbon by itself. We don't have just sodium by itself. We have these things put together. And that means we're going to call it a compound. There are far more compounds than there are elements. So elements, we know there are 118, or rather to our best knowledge and our best theories, there are 118 and no more. But with compounds, there are millions and millions and millions of them. So tons of different compounds. Most of them are organic compounds, meaning they're carbon-based, which is stuff that you'll talk about in organic chemistry. But we're going to see that putting elements together, you're going to get a lot more combinations than just having elements by themselves. All right, so do we see the difference between an element and a compound? Elements have one type of atom. Compounds have multiple types of atoms within them. And so that's the distinction we're looking for there. Alrighty, so now finally to answer Michaela's question, we're going to take a look at that mixture idea again. Let's go back to dark blue here. We're going to see that often mixtures are going to be multiple compounds put together. Technically, you could have multiple elements as well, but since there are far fewer elements than there are compounds, I mean, we'll throw that on there. Typically, we're looking at multiple compounds. And so, for example, if we take a look at salt water, well, I mean, we think of that as just one thing, right? We think of salt water. You go to the ocean, you take a glass, you have a thing of salt water, right? Although that salt water is going to have a lot more than just this, but that's got two compounds in it, right? It's got sodium chloride or salt, and it's got water in it, right? It's got two compounds now. So salt water is going to be a mixture because it's got multiple compounds going on. If we say my coffee, well, it's certainly got water in it, which is a compound. It has caffeine in it, which is a compound. And it's got many other compounds. Theobromine, various xanthines, all sorts of alkaloids, lots of stuff going on in the coffee. But we're going to see here that any mixture is going to have multiple elements or compounds put together. Something like, I don't know, a cookie will have, it'll have sugar in it, it'll have probably gluten, which is a protein, which would be a compound. We have all sorts of other things. We've got various fat molecules. We've got water in there. We've got probably some baking soda in there. We have maybe some, if we've got chocolate in it, we also have caffeine. We have tons and, hundreds of compounds in a cookie. So that's a mixture too. Tons of compounds. Steel will also be one, as I mentioned, although this is a combination of elements instead, not as common as combinations of compounds. This has got iron, which is an element, plus carbon, which is an element, plus, what else do we have? Nickel, we'll say, which is another element. And if we wanted, different types of steel, we'll have different other random elements in there. But those are also, the steel is also a mixture. And so I think Michaela might have had the question of, like steel, we kind of see it as one thing. We have multiple elements in there, but it's not a compound, even though it's only made up of elements. And so that distinction is a little bit harder. We're going to see that these elements in steel are not chemically bound to each other. So if we wanted, we could separate them pretty easily. However, if we wanted to separate the sodium and the chlorine in salt, we have to put in a ton of energy to get that to happen. And so it's not as kind of easy to separate them because the sodium and the chlorine are bound together chemically. So that's kind of the distinction there, perhaps. But suffice it to say, generally, mixtures are going to be more often than not, far, far more often than not, mixtures of compounds. So hopefully that'll make it easy. If you can think for something, salt water, for example, salt and water, two compounds, it's a mixture. And so we're going to see that uh, mixtures are most things that we deal with in real life. After that, it's compounds, and after that, it's elements. So kind of we're looking at our biggest category last year. All right, hopefully, Michaela, does that help that out? Alrighty. In the meantime, let's talk about mixtures some more. Great. Okay, so it turns out we can also classify different types of mixtures. And so we're going to see that we can have what are called homogeneous mixtures or heterogeneous mixtures. And we're going to see that for something to be a heterogeneous mixture, it is all the same throughout. So, like salt water. Generally, if you are crazy and drink the salt water, if you were to take your metal straw and take a sip of salt water from the top of the glass versus the bottom of the glass, they should be the same. They should taste the same, as disgusting as they would be. Um, that's an indication that it's homogeneous. It's the same throughout. It looks identical no matter where you look. If you were to take a sample from various parts of that mixture, they should all have identical composition. So they should be the same throughout the mixture. Something like air generally is also homogeneous. Air is going to be about 78, 79% nitrogen, 20-ish percent oxygen, 1% argon, no matter where you are on the earth. There might be some subtle, slight differences. For example, if there's a fire burning right outside now, you've got smoke in there or something, you got more carbon dioxide. Slight differences, but generally we consider air to be homogeneous uh, in the grand scheme of things. So if you take a breath where you are now, and if you go over to Ireland and take a breath there, your body doesn't explode because the air it's breathing in either location is essentially the same composition. So that would be kind of awful though, right? Like imagine if you had to travel and your lungs had to get used to different amounts of oxygen in different areas. It would be it'd be very tough. So I mean that's already a pain with altitude. Even though the composition of the air is the same at altitude, you just have less of it. So uh, well that's anyway, that's biology. We'll get into I don't have to deal with that, so you guys can talk all about your bisphosphoglycerate adapting to altitude and that sort of thing in physiology class. Yay. A heterogeneous mixture, these are easier to identify. Yeah, is it right now? Okay. I'm not in, I'm in LA right now, so I'm escaping it. That's good. Although I'll be going up to Ridgecrest tomorrow, so. No, Thursday. I'll be going up Thursday. So hopefully it'll be clear by then. So yeah, that could be, there we go. Here we go. Smoky air. Because now you have particulates in it. And so, because you can see the smoke too, right? One, classic indicator of a homogeneous mixture is you can't really see any differences. But if you are apparently in the Kern River Valley right now, yikes, then yeah, you can see columns of smoke probably. One breath might be, Jesus, really? All the way in San Francisco? Wow, yikes. Big fire then. Yikes, 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 yikes. So, not a good thing. But there you go, you can see it. That indicates it's heterogeneous. So, you're going to see a column of smoke. You might take one breath, it's not so smoky. The next breath, very smoky. Could vary from time to time. That's heterogeneous there. So you have now something else in there that's not evenly distributed throughout. 16,000 acres, yeah, that's, sorry, yikes. Hopefully they'll get that contained soon, but I know we're right in fire season, just about, so yikes. Another example would be something like a salad. If you take a bite of salad and you have your next bite of salad, it's not exactly identical to the one before, right? Maybe you had a crouton this time, maybe you had a tomato last time, maybe you had one drop more dressing this time. Uh, that's a heterogeneous mixture. Your cookie is going to be up here as well. Uh, so we're going to see that things that have different composition in certain areas are going to be heterogeneous mixtures. Ice water would be one too, because you have got ice floating on top, water on the bottom. Generally, the icy part is going to be colder than the bottom part, so you not only have differences of having, um, now chunks of ice in one part, you now have a colder bit of water on it. Yay! Well, hopefully well, I hope the wine country is not burning down again. I feel like they've had their fair share of misfortune in the past couple years. So, but that's cool. So, I mean, it's not cool, but it's cool to have people all over California enrolled right now. I think that's pretty cool. Um, but interesting thing about ice water, ice is water, right? They're the same thing, chemically speaking. So ice water is the same compound, but in different states of matter, and that's still going to make it a mixture. So that's something interesting there. So we'll put that in purple, because why not? We have solid and liquid water there in ice water, and that's going to be a heterogeneous mixture. Even though they're the same compound, we still would consider them separate because they're not exactly identical to each other. Let's see some other homogeneous ones while we're here. Honey would be one, assuming it hasn't like crystallized all over the bottom. Honey is a mixture of um, various sugars and water, mostly fructose, some glucose in there as well. Maple syrup would be another one. This is again assuming it's not like an old bottle where you have this kind of crusty stuff happening as crystallized sugars crystallize. That would then make it heterogeneous. Something like olive oil would be a heterogeneous mixture, or canola oil, whatever oil you like. Uh, Motor oil, gasoline. No, yeah, gasoline would be one too. But main thing is soy sauce. Yeah, for sure. Definitely a homogeneous mixture there. So, main easy way to tell the homogeneous mixture is just kind of look at it. If it looks the same throughout, it's probably a homogeneous mixture. So if you look at your bottle of soy sauce, it's not darker at the top and lighter at the bottom. It doesn't separate like that. So, you know, that would still be a homogeneous mixture. Um, Something like what separates pretty that you need to take up? Oh, salad dressing. Something that separates, or like if you've not had your peanut butter in a while and the oil's kind of separated out, that would also be heterogeneous because now you have two different kind of layers there. So hopefully, um, again, nothing too difficult here in terms of identifying kind of bits of matter. Alrighty, kind of an important bit here. All pure substances are homogeneous by default, right? If you're just looking at sugar, There's no area of the sugar that's different. It depends. That's so it's probably a suspension, the juice that you're talking about. I'm thinking if you like leave it out long enough, it probably would separate, right? Um, and it also depends if there's like pulp or anything like that in it. Um, then it would be heterogeneous. So even though yeah, it may look the same kind of visually, that's the kind of quick and dirty method of identifying it. If you really want to be precise, you have to like molecularly go in and see is everything distributed exactly as it is. So, um, you know, that also includes over time. Like if you just leave salt water, let's say it's in a jar, so it's sealed, so there's no evaporation. Um, it could, it really just depends on the juice, right? So, uh, if the juice is really, really filtered, super filtered, and it's kind of transparent, you can see through it, it's probably going to be a homogeneous mixture. But if it's something more like the V8 type of juices or naked juices, those most likely, yeah, coconut water would be homogeneous, I would say. Um, I mean, you don't really have pulp or anything in coconut water. Uh, I I think. I don't. It's usually in a like not see-throughable container. So just thinking though, typically yeah, I would think coconut water would be homogeneous. So, but you're kind of like more rustic juices are gonna probably be heterogeneous, depending. Like if you have pulp in them of any sort or any fibers. Yeah, kombucha would probably be heterogeneous. That's a good example. Or we could even say soda, because kombucha you have just a little bit of fizz, right? Uh, just as a result of the fermentation process, and so just having multiple phase states of matter in there would make it heterogeneous. So if you leave your kombucha out and it gets, or I mean, it's not really super fizzy to begin with, right? But um, if you completely let that do its thing, it probably might be homogeneous eventually, but it just depends, right? So, anyways, let me finish this thought about this thing. So we kind of don't uh, use that term with pure substances. So if I'm asking you to classify something and you say, okay, here's my hydrogen gas, if you say it's a homogeneous element, you're going to see that chemists are particularly anti-redundancy. We don't like to say the same thing twice. So, I mean, while technically, yes, sure, it's homogeneous, we would never say that. Not necessarily. So, let me see. Do I have an example of something homogeneous in here? Um, so just the fact that it has multiple ingredients just means it's a mixture, right? So having, salt water has got two ingredients, salt and water. Uh, that is going to be homogeneous, right? Assuming all the salt has dissolved in it. If you have salt crystals at the bottom, it's heterogeneous. So it just has to depend on um, kind of if everything is dissolved, if everything is molecular, like you know, carrot juice technically just has one ingredient, right? It's got carrots. and that's it. But carrots are already a mix of all these different compounds. You have, cellulose, you have glucose, you've got beta carotene, whatever. You've got all these different compounds in there. But carrot juice, I would say, is probably heterogeneous because you just throw it in the blender or the juicer, right, and you still have bits of carrot kind of in there. Not really big ones, but they're there, and so uh, it would probably be heterogeneous there. But something, even if it has 200 ingredients, could still be homogeneous. Like my tea here. Well, I guess this is a bad example because I have like little bits of leaves in there. But let's see. Let's see. There we go. Into the tea. So my tea here, ignoring the like little flowers or leaves or whatever at the bottom, it's got hundreds of compounds in there, hundreds of ingredients, and so hundreds of ingredients doesn't make it heterogeneous. So this is, I would say, homogeneous, pretending those little bits at the bottom aren't there. Had I been more careful with my straining of it, it would be really homogeneous. So, um, but I think at this point we're getting a little nitpicky. So, thankfully for the things that I will give you, they should be obvious. So, um, I'll make it so we're not looking kind of microscopically at these sorts of things. So it'll be like the salad. Okay, that's obviously heterogeneous because we can see different parts of it. Uh, but anyways, back to this. Don't use the word homogeneous when talking about pure substances. It's redundant and it makes chemists mad, apparently. So we just don't do that. So if we were to describe hydrogen, the best way to describe it would be to say it is first off, it's a pure substance, and it's an element. So that's kind of the bigger category than the smaller category. There. So that would be the best way to talk about that. If we were to talk about water, the best way to describe that would be we would say, okay, yeah, it's a pure substance because it's just one thing, and in this case, it's a compound. And then if we were to say our salt water, generally that should be a homogeneous mixture. And if we were to say, what's another good example? How about a salsa? That would be a heterogeneous mixture. So, just think of your typical salsa mexicana. It's got tomatoes and onions and cilantro and maybe scallions and jalapenos, whatever, chunks of stuff, right? You can see very clearly, there's a tomato there, oh, there's an onion there. Heterogeneous mixture. Salt water, it's essentially the same. Miss Jersey, you stop that. Oh, so naughty. We have a naughty doggo. She's eating my notes from something. Well, here we go. Here's our first doggo meeting of the semester. This is Miss Jersey. She is about an 8.5 or so year old Chihuahua. Very naughty. She's probably going to be the one who's going to be barking the most as we get into things. So, she loves to eat paper. She has eaten a paycheck before, hasn't she, Miss Naughty? Yes, you are. You're so naughty. Okay, back you go. She is probably also the one who spends the most time with me. She likes to be in my office, so that's probably the one you'll see most often. So we'll see as we go through the semester. Maybe we'll see all of them. Doubtful, but we'll see. I have 9 dogs, by the way, so if we see all of them, it will be indeed a miracle. So, alrighty, so that's doggo number 1. Alrighty, so let's do a couple of examples here. Let's say most of my dogs are also old Chihuahuas because find them on the Pet Finder or whatever, and it's like nobody wants them, and I'm like, oh my god, no. Okay, but anyways, let's get through this. Let's do a couple of examples. So let's say we have ba, 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 ba. Oh my god, she's got another piece of paper in her mouth now. Let's say we have a couple of things. Let's try to classify these. So let's say we have a cell phone. Let's say we have helium. And let's say we have vinegar. And for this vinegar, let's just say it's plain old white vinegar. It's not one of the kind of more like natural vinegars that has all the yeast and stuff at the bottom. Just plain old, if you're going to be cleaning with it, vinegar, that sort of the cheap one. Cheap white vinegar, distilled vinegar. Yeah, let's say distilled. And just for your information, I'll tell you that in case you're not familiar, I'll put some information there about the distilled vinegar. Let's talk about these. Let's try to classify them as best we can. So first, let's classify as a pure substance or a mixture. So, if we're looking at the cell phone, do we think that is a pure substance or a mixture? Ta-da, here it is. Is this thing a pure substance or a mixture? Hopefully, should not be too difficult. It certainly is a mixture, right? Let's do this in a different color. How about we use green this time? Right. We have all sorts of different things on this phone, right? We have a battery inside that has lithium and cobalt and other and lovely juices. We have, glass on the top. We have silicon processing chips. We have all sorts of fun stuff in there. All right. Just doing the one classification now. So looking at helium, is helium going to be a mixture or a pure substance? So if we go to buy a gas tank of helium, or we just go to get a balloon filled or something, we're going to see this one might not be as obvious to you yet, but hopefully we'll see that that's going to be indeed a pure substance. Exactly. Exactly. It's one thing only. Whereas the cell phone has many things going on. All right, and how about the vinegar then? So hopefully this is made obvious by the fact that I've given you some information there about what is in vinegar. And so, is vinegar going to be a mixture or a pure substance? Yes, indeed, mixture. We see here we have acetic acid, that's that first compound there, and we have water. That's what's in vinegar. That's going to be two compounds makes it a mixture. All right, so now going one step further, back to the cell phone. So now we know it's a mixture. Is that mixture going to be heterogeneous or homogeneous? Is my cell phone exactly identical throughout, or are there little bits and pieces that are different from each other? Again, hopefully not terribly difficult here. So we'll see. Very good. This is a heterogeneous mixture. So it's got all sorts of different bits. It's got a camera, it's got battery, it's got computer chips has got little wires and stuff. All those are different, right? So if I want to look at just the top, I might look at the camera. But if I look over here, now I just have the screen. I don't have any camera anymore. So it's going to be a heterogeneous mixture. It's not the same throughout. All right, helium time. So we have identified it is a pure substance. Oh, I guess I should put step 2 here. 2A. Classify a pure substance as element or compound. Or step 2B, classify a mixture as heterogeneous or homogeneous. Okay, so with our helium, we have to ask ourselves, is helium an element or a compound? And you might not know this, and that's okay at this point. We're going to see that the answer to this question is, can we find it on the periodic table? And so that's kind of our cheat sheet, because you're probably, not familiar with every single element. You will eventually be, but, well, not every single one. But we're going to see that helium is an element. And we can tell that it's an element because it's on the periodic table. Let's see. How do we know that? Okay, let's go find my periodic table, which now I have to find here. Here it is. Okay, periodic table. Not something we're going to necessarily have to deal with yet, but if we're trying to figure out if something is an element or a compound, the best thing to do is take a look at the periodic table of elements, which lists all of our elements. Oh dear, look, it's already got 2 more. It's already got up to 120. So in the past, 3 months or whatever, people have decided we're going to throw in some period 8 elements. Oh dear. All the way to 127. Yikes. Chemistry is continuously getting better, I guess. Anyways, helium is way up here in the top right. And so, because we can find it on the periodic table, we're going to be able to identify it as an element. That's what we're looking for here. So, notwithstanding the fact that I've just lied to you about 118 elements, there's 118 known elements. I guess now there's 127, or an additional 9 theoretical elements. Anyways, enough of that. Let's do the vinegar now. We've identified it as a mixture, plain old white vinegar. We're going to see that one is going to be a homogeneous mixture. Because that vinegar is going to be the same throughout. If you have some kind of if you've got one of those natural apple cider vinegars or whatever, you'll probably see some goopy stuff at the bottom. That's the yeast there, the mother. That would make it heterogeneous because now you've got goopy stuff at the bottom in there. But if it's been filtered, then it's probably homogeneous. Or distilled, that's another way to separate things. So there we have it. Alrighty, any questions on these 3? Again, hopefully not too difficult. Alrighty. Oh, by the way, if any of you have any difficulty with, so the colors I typically use are these kind of upper row ones here. So I typically use 2 different shades of blue, black, green, and purple. If any of you have any trouble distinguishing those, I don't really make, I'm not going to throw questions at you where it's is it the lighter blue one or the darker blue one, but just in case any of those are difficult for any of you to see, just let me know, shoot me a message on Discord or something, and I will avoid using one of those if it's of difficult visibility. But I typically find these are usually okay. So, and I just like to use different colors because it's pretty boring to just have black text everywhere. So uh, just be aware of that. Cool. Alrighty. Next kind of little section here. Alrighty, let's talk about properties of matter now. And those are going to be kind of characteristics. So when we think about matter, we might want to describe it to each other. And often we do so all the time. Uh, you know, if you want to identify something, you might talk about its properties. And so if you want to distinguish something from another piece of matter, you'd want to say what makes this particular bit of matter stand out. And those would be properties that you'll talk about. Now, most often these are going to be physical properties that we're going to talk about. These are going to be measurable ones. Things we can identify or measure about something. And some really kind of easy ones for us, switch of colors again. Something like size, or color, or shape are easy things we can talk about matter if we want to distinguish it from each other. If I have, say, a cork and a stylus, if I want to distinguish between them, I could say, oh, I'm talking about the little brown thing, or the thing that is shaped like a mushroom, or the smaller one. I might say, okay, yeah, I'm meaning this one, right? If I'm just distinguishing between things, right? Um, I might say also the location of it, the one in my right hand, if I want to describe something, describe a bit of matter. These things are pretty easy to tell, right? We can say, oh yes, it's big, it's small, it's over there, it's triangular in shape, whatever it is. These are properties of matter that we can identify. And these are all physical properties, things that we can measure. Some that we might also talk about is the state of matter. Is it a solid, a liquid, or a gas? We'll talk about states of matter later on. What else can we identify about matter? We could say kind of the amount of it as well. You know, am I talking about the big pile of sand or the small pile of sand? Or I could go a little bit more scientific on you. We could talk about things like conductivity. Which one of these things conducts electricity or heat better? These are properties that we could talk about. Or melting point. At what temperature does it go from solid to liquid? Or vice versa. Or boiling point. These are all physical properties. We could talk about its compressibility. You know, for example, we might have something like a sponge that we could very easily squish. Or we could have a brick, which is very hard to squish, right? We can press all we want on that brick, and it's not going to squish. But we press even a little bit on the sponge, and it squishes. Or we can talk about, I don't know, strength. At what point does this thing break after we apply some sort of force to it? Toughness. We could talk about all sorts of various physical properties here. The big thing, though, is that we can measure them. We're going to see that if we want to identify something as a physical property of matter, we want to be able to measure it or have something to say about it. We want to be able to describe it. And so these would be physical properties, stuff we can measure. By contrast, we have chemical properties. These are not so obvious to us. And chemical properties deal with the question, will something react with another thing? And perhaps the most easy example for us would be is this thing flammable? That would be a chemical property. So we could say, okay, yes, this wood that I have here is flammable. That's a chemical property of the wood. Physical properties of the wood might be something like it's brown, it's shaped like a log, it's got a certain texture to it. It doesn't conduct electricity very well. But if we want to talk about its chemical properties, that's asking, will it react with something? And the most common one is, does this thing burn or not? And that's asking, does it react with oxygen? But something like, I don't know, how about water? Is water flammable? No, it's not, right? So water and wood are differing in their chemical properties. They're also differing in their physical properties, right? We know water is going to be generally a liquid. It's going to be clear. It's going to have its own properties, whereas the wood is typically solid and has its own things. So we can talk about chemical properties of things as well. And so most of the stuff that we're going to talk about for the first half to 2/3 of the semester are physical properties. And then we'll talk into chemical properties towards the end of the semester when we start talking about chemical reactions. Another question that we might ask is, will X corrode over time? Will it rust? And we'll say, oh, well, if we have iron, yeah, that'll rust. But if we have something like aluminum, probably not. Aluminum does not react as easily as iron does, at least in terms of corrosion. So chemical properties they're kind of just asking, will this substance, whatever it is, react with this other substance? And so that's the question that we're answering with chemical properties. So it's not something we can measure. We've got to figure it out experimentally, usually. So we usually then combine them and say, did anything happen? We'll have to find out. So that's kind of how we might talk about characteristics of matter. We can describe its physical properties, we can describe its chemical properties. And the more information we have, the better we're able to kind of predict how it's going to behave in certain situations. So, for example, we know Kevlar, the material in bulletproof vests, is a very strong material, right? And so we're going to predict that, the more we have of it, the better kind of a protective shield we're going to have, because it's a very strong material, it can resist impact and pressure being applied to it. So by understanding its physical properties, we can kind of make applications out of it. And if we were to say, okay, we're designing some wiring for a new house, do we want to choose this copper wire that conducts electricity very well, or do we want to make wires out of wood? Which would be really stupid, but we've already addressed these questions, but we would think, okay, let's think which one has the better conductivity. And we might also want to say, okay, well, if I try to run electricity through the wood, it's actually going to probably burn. So that's probably not a good idea because it's going to react with the oxygen in the air. But if we heat up some iron or copper, it's not going to react with the water, or I'm sorry, the air around it and start burning. So these are important questions, right? So it's kind of all about the application for these. But those are our characteristics of matter that we'll use to distinguish them from each other, at least scientifically. Alrighty, any questions on that? Generally, again, Um, when it comes to chemical properties, most often the kind of standard example is flammability or combustibility. Oh goodness, combusta. Nope. Combustibility. I think that looks right. Yeah, I don't think it has an A. It's an I would say. English is stupid that it doesn't have consistent words. But anyways, and then this would be corrosion. I hate using parentheses before words that begin with C. It drives me nuts. So these are two examples of chemical properties, probably the most common two examples. All right. It turns out that matter can also undergo change, right? So we're talking about matter, right, and its changes in chemistry. So when we talk about matter, we're talking about the properties of it. We talk about all these kind of physical properties. These are only a few. There's tons more physical property wise. Basically, anything you can measure is going to be a physical property, whether that's measuring with your eyes or with some instrument. That's going to be a physical property about it. Chemical property is harder to do. You have to do experiments mixing things together to see if they'll react. Uh, but that will lead us into now that we've talked about matter a little bit, talked about classifying it, talked about how to talk about it, we can talk about changes of matter now. And when matter changes, we're going to see that it breaks into two categories. That seems to be the theme of today. Break everything into two categories, right? We're going to see that the first one would be physical changes. And these are going to be defined as altering a physical property. Of the material, whatever you're doing. These are also generally reversible, and they do not alter the composition, what makes it up, of the substance. So, easiest physical change of all. Stylus in my right hand is moving to my left hand. I have changed its location. All right, so I've changed one of its physical properties. It has just undergone a physical change. Note this is reversible, right? I could put it back in my right hand fairly easily. And after this change, it's still a stylus. I have not changed the material itself fundamentally. Another example, I could take this paper, whatever this is, and fold it in half. I have changed its shape now. I could unfold it. Ta-da! Now it's back to the way it was. And if I ask myself, is this thing still paper? It is. So, that's a physical change, right? Or if I crumple it all up and do something like that, it's still paper at the end of the day. So, I'm not altering the composition of the substance through its physical change. But if we undergo what's called a chemical change, well, I guess I should give an example. So there's your example. So moving something or changing its shape or whatever. Or actually, let's do another example. Another example would be ice melting. The physical property I'm changing there is its state of matter. So if I have an ice cube solid water, right? If I allow it to melt, I now have liquid water. That's going to be a physical change because I'm messing with its physical property. It was a solid, now it's a liquid. State of matter is a physical change, right? Is it still water? It is. It is still H2O, right? Unfortunately, we say water for both the liquid and then for the entire compound. So, but it's not changed, right? And if I want to, I could put it in the freezer. Now it's ice again. So I can reverse that fairly easily as well. And so this is another example of a physical change, right? We're changing the state of matter. We're going from solid to liquid water. And that is a physical change. All right, I can go back if I wanted to pretty quickly or easily, and it's still water at the end of the day. Alrighty, let's do some chemical changes. These are going to be the opposite. So these will alter the composition of the substance. These are going to be either impossible or extremely difficult to reverse. For example, if I take our log, I'm going to actually do some coloring here because why not? And now I've burned it. That's essentially saying that I'm taking some we'll say it's sugar based, which it probably is. All the cellulose and all the fibers and all that are all sugar based. But that's essentially becoming two different things, right? We're taking, we'll say wood or glucose, sugar, sucrose in this case. We're adding oxygen to it, and we're coming out with two different molecules out of this kind of reaction here. And so if we do that, we end up with now carbon dioxide and water molecules after we've burned our log. For the most part, there's other stuff going on too, but by and large, it's mostly those two. If we were to just take carbon dioxide and water and put them together, do we get a log back out? No, right? It's essentially impossible for us to take those end materials and reverse this process, right? I mean, to take two gases and put them together and poof, here's a log, not likely to happen, right? Plants can do it. Takes a very long time, but they can do that. But it's still not going to be exactly the same log as it was before, right? So where I could get exactly the same ice as it was before, if I were to freeze some water or something. So this will be an example of a chemical change. I'm fundamentally changing my material by turning it into something new. I'm turning my wood into carbon dioxide and water. And so those are now two new compounds. We've altered its composition. It's no longer wood after this change took place. Remember, if I bent the paper, it's still paper. That's a physical change. But if I burn the paper, it is no longer paper at the end of that. Yeah, right. That would be very nice if we could do that. So unfortunately, that's not the case. So, but yes, that's the idea here. A chemical change, the hallmark of it is that it's different at the end. Whereas a physical change, it's the same at the end, chemically speaking. So if you boil water, it turns into water vapor. Both of them are still H2O. If you take paper and burn it, you go from cellulose to carbon dioxide and water. And so and ash and all sorts of other stuff, but not going to be reversible here. So unfortunately, or rather, that's how we'll distinguish these. So we can talk about how we might have matter changing as well, and we can classify those changes. So most of these are going to be chemical reactions here. Chemical reactions essentially are chemical changes. So again, we're going to talk mostly about physical stuff for the first half-ish of the semester, and then we'll talk about chemical stuff for the second half. So matter and its changes, right? So we'll be going through that. Alrighty. I think we are at a good place to stop for the day, a few minutes early. But I'm ready to give us our participation prompt for the week. So again, for the first 2 weeks, I am obligated by the state of California to make sure that you are participating. And since again, this is a fully online course, so no attendance as it is. You guys do not have to show up for these live recordings. You're welcome to watch them later and then just skip over when I start dabbling about whatever I did, 2,3 bisphosphoglycerate, I think, earlier, whatever. You're welcome to do that. How we participate is going to be a little different. So, a lot of you, at least in 111, have done this already, which is fantastic. I didn't have to prompt you at all. But if you haven't done so, you must now introduce yourself on Discord. That is our participation for this week. So in order for me to satisfy the state's requirement that you are participating for the first 2 weeks, for this week, all you have to do is introduce yourself on Discord. So if you're in, so 101 and 111 are together right now because again, same material. You're going to go to your general tab, I guess, or channel, and you're gonna say, "Hi, I'm blah blah blah," and just this is a sentence. It's nothing onerous, right? It's just introducing yourself. So, again, in case you guys are not familiar, let's pop open. Do I have Discord open here? I do. Good for me. All right, this is not necessary. So, if you're in 101, just remember at the bottom here to get access to 101 or 111, you have to click the animal of choice below. So if you're 101, you're clicking the frog. If you're 111, you're clicking the camel. After you do that, you'll see poof, now you have access to channels here. You're going to want to click this and just say something. Hi, I'm Michaela or whatever, and ta-da. Just, something, maybe something interesting about yourself, or, we have a lot of people at different colleges. It might be like, hey, I'm at Porterville, and, this might be something nice like that. Same thing here, but as you guys have somehow already done, everyone has done a ton of stuff already here, which I'm super proud about. That's awesome. I didn't have to prompt anyone, and already like 40 of you have said something. So if you've already done it, you're okay. You don't need to write anything else. So you're good. I'm just looking for your name somewhere on this page, and that's all I have to do. So that's kind of our participation requirement for this week. Okay, so you're going to do it in one of these, whichever class you're in. Just say hi, introduce yourself, and that's all you have to do. Alrighty, so, and then of course, again, if you want to share photos of your pets, or if you find it amusing meme, go ahead and share those. Uh, I typically will be sharing interesting chemistry memes as I go through, or just general school online in general ones. I find those pretty fun. So, alrighty. Also, if you have any questions at all, throw them in the same channel on Discord. Probably a good idea though to tag me, if just because there are a lot of you. If you want to get my attention, what you should do is you'll do the @ symbol. If you just, am I Professor G? I don't remember. I think so. If you do that, let's see, does it work? Why is this not working? Oh, okay, well, apparently this tablet refuses to do it. But if you want to ask me a question, best way to do that is to tag me by doing the @ symbol and then Professor G. That'll be the easiest way to do it. So, if you want to ask me a question, you can ask me whatever you like. If you what's my favorite color, go ahead. I'll answer you. So, again, Discord is our main area of communication. So, it's the fastest way to get a hold of me. You'll see that I'm often on Discord essentially all the time. So you'll generally get a response pretty quickly. So you see David here has tagged or pinged me. So that's how you do it. So if David wanted to get my attention, that's how he'd do it. So and then there you go. And then I will angrily, grumpily react. Oh, I can't do it on this tablet, but uh, I'll be able to say yes. Oh, God, this tablet is so annoying. Okay. Sorry, I don't typically use the tablet for this, so. Um, but there you have it. That's how to get a hold of me pretty easily. So, and again, Discord's super casual. You do not have to worry about your capitalization and punctuation and whatever, as long as people can, make sense of what you're trying to say. It's essentially just, chatting, texting, instant messaging, whatever. That's what this is. So you do not have to be formal on Discord. Generally, it's easier if you do want to email me for whatever reason. It's easier to read if they're more formal. I guess we have that kind of psychological thing. But Discord, go ahead, be as casual as you want. Go ahead and put your gifs. Did I just say gifs? Hopefully that makes some of you mad. So if you do that, good. Alrighty. Well, that's it then. So I'm going to go ahead and upload this onto YouTube. So I guess that doesn't really matter to any of you who are here now, but it'll be up there forever if you'd like to rewatch this. You can also just see it on Twitch as well. It'll have all my videos, though it only stores them for 2 months before it deletes them. So, coolio. See you on Thursday for our next video. So again, all you have to do, introduce yourself on Discord, and that's it. We're not going to have any kind of like hard assignment this week. So, alrighty. Take care, everyone. See you Thursday.